In today's video, we will discuss about the application of Rolle's theorem. So what is Rolle's theorem? Rolle's theorem states that if a function fx is continuous in the interval a comma b, interval closed, and it is also differentiable in the open interval a comma b, and f of a is equal to f of b, then there exists a point x equal to c in a comma b for which f dash c is equal to 0. Mathematically we can write Rolle's theorem if fx is continuous on a comma b comma differentiable in a comma b, and f of a is equal to f of b, then there exists at least a point x equal to c in a comma b such that f dash c is equal to 0. That is, the function must be continuous in the interval a to b, here x equal to a, x equal to b. I have already discussed this topic in my video lecture. So these points are f of a comma f of a, and this point is b comma f b. The function is continuous in the interval, and it is also differentiable at each and every point on this curve. Then there exists at least one point x equal to c in a comma b for which the tangent at the point x equal to c is parallel to x axis, that is, its slope will be is equal to 0. So f dash c is equal to 0. Now we need to solve some problem to understand the application of Rolle's theorem. Your number one problem is verify Rolle's theorem for f of x is equal to x square minus 5x plus 4 on the interval 1 comma 4. Here a is equal to 1 and b is equal to 4. So given f of x is equal to x square minus 5x plus 4. See, this function is a polynomial function. So since f of x is a polynomial function, therefore it is continuous on 1 comma 4. We know that all polynomial functions are continuous on capital R, that is, at each and every point of the real number the function will be continuous, that is, there is no point of discontinuity. So your function x square minus 5x plus 4 is a continuous function, that is, for each and every value of this interval 1 comma 4 there exists a functional value, that is, for x equal to 1 it is something, for x equal to 4 it is some image, that is, it is not discontinuous at any point in the interval 1 comma 4. So it's a continuous function. Now if I find the derivative of fx, for x square the derivative is twice x, and for 5x it is minus 5 into 1, for 4 it is 0. Now you can see the derivative twice x minus 5 itself a polynomial function. Again f dash x is also a polynomial function. So that means in the interval 1 comma 4 the value of f dash x is always continuous. So we can say that therefore f of x is differentiable. F of x is differentiable in 1 comma 4. When we say a function is differentiable in the interval, that is each and every point in the interval you can draw a tangent on this curve. So in the interval 1 comma 4 and at each and every point in the interval we can draw a tangent at this point, because if I put x equal to 2, x equal to 3, x equal to 3.1, etc., the value of f dash x is defined. So we can draw a real tangent at each and every point in the interval 1 comma 4 except the boundary points. So it is differentiable in the interval 1 comma 4 open interval. Now f of 1, put x equal to 1, you will get 1 minus 5 plus 1 minus 5 plus 4, it is 0. And similarly for f of 4, it is 16 minus 20 plus 4, again it is 0. So your f of 1 is equal to f of 4. So now the each and every condition for Rolle's theorem the function satisfies. Okay, so it is continuous, second it is differentiable, and third case is f of a is equal to f of b. Therefore we can say that hence Rolle's theorem is applicable. Therefore there exists at least one point x equal to c in 1 comma 4 for which f dash c is equal to 0. Now if I place the value of x equal to c in your f dash x, I will get 2 into c minus 5. The value of f of x is equal to twice x minus 5. If I put x equal to c here, I will get twice c minus 5 equal to 0. Therefore the value of c is equal to 5 by 2. What is 5 by 2? It is 2.5. That means it belongs to the interval 1 comma 4. So it is verified that therefore Rolle's theorem is verified. If the value of c is lying in the interval 1 comma 4, then it is verified. Other than we will say it is not verified. Here comes the second question. You have to verify Rolle's theorem for the function f of x is equal to x cube minus 6x square plus 11x minus 6 on the interval 1 comma 3. So first case, it is a polynomial function, so it will be continuous everywhere. So you can write, given f of x is equal to x cube minus 6x square plus 11x plus 6. Since f of x is a polynomial function, therefore fx is continuous on the interval 1 comma 3. Now find out the derivative of f of x. If I differentiate f of x, I will get, for x cube the derivative is 3x square, for x square it is twice x, so 6 multiplied by twice x, it is 12x, and for 11x it is 11 into 1. Simple. So I am getting 3x square minus 12x plus 11. Again f dash x is also a polynomial function. Therefore, f of x is differentiable in the interval 1, 3. Now, we'll check the value of f of x in the boundary points, that is 1 and 3. So, what is f of 1? See, for f of 1 it is 1 minus 6 plus 11 minus 6. The result is 0. And what about f of 3? It is 27 minus 54 plus 33 minus 6. Simply it is again 0. So therefore f of 1 is equal to f of 3. So it satisfies all the conditions of Rolle's theorem. Hence Rolle's theorem is applicable for the following function. So therefore there exists at least one point x equal to c in 1, 3 for which f of c is equal to 0. Now if I place x equal to c in your f dash x, I will get 3c square minus 12c plus 11 is equal to 0. Now it's a quadratic expression, so you can solve it the formula of minus b plus minus root over b square minus 4c by twice a. So here a is equal to 3, b equal to minus 12 and c equal to 11. I can put minus b. So b equal to minus 12 minus minus plus minus b square, 12 square is 144 minus 4ac, 4 into 3 into 11, 4 into 3 into 11, it is 12 into 11, it can be 12 plus 12, it is 142, 132. So plus, this is minus 132 by 2 into 3. So result is 12 plus minus root over of 12 by 6. So 12 plus minus root over 12 means 2 root 3 by 6. If you divide by 6, I will get 2 plus minus 1 by root 3. 2 plus minus 1 by root 3. Now, these two values, 2 plus 1 by root 3, it will be in between 2 and 3, and 2 minus 1 by root 3, it will be in between 1 and 2. So both the values belongs to the interval 1, 3. Therefore Rolle's theorem is verified. Now let me draw the figure for your better understanding. This curve f of x is equal to x cube minus 6x square plus 11x minus 6. This curve or function x cube minus 6x square minus 11x minus 6 has 2 points where f dash c is equal to 0. That means if I draw the y-axis and x-axis, this point is 1, this point is 2, and this point is 3. For x equal to 1, the functional value is equal to 0. For x equal to 3, it is again 0. So at 1 it is 0, for 3 it is 0. Again for 2 it will be 0. If I put x equal to 2 here, for 2 it is again 2 cube minus 2 square into 6, 24, 2 into 11, 22 minus 6, you will get it is 0. So the function has graph like this. at this point is 2 minus 1 by root 3. Here the graph has a tangent parallel to x-axis. Similarly, this point is 2 plus 1 by root 3. It is in between 2 and 3. At this point, if you draw a tangent, it will be again parallel to x-axis. So there exist 2 points where the tangent is parallel to x-axis. So I have already told you, for Rolle's theorem, when a function is continuous in the interval a comma b, it is also differentiable in the interval a comma b, and f of a is equal to f of b, then there exists at least one point, at least one, I said at least one, now I am getting at least one, 2 points here, there are 2 points, more than one, it is possible. So this is the geometrical interpretation of this problem. Now second question is, show that Rolle's theorem is not applicable for f of x is equal to x to the power 1 by 3 on the interval minus 1 comma 1. See, it is not a polynomial function, but x to the power 1 by 3 is there. Now the radical is odd number 1 by 3. So for negative values you can also get real values. But if it is square root, then we could have said for negative values the function will be undefined. But it is 1 by 3. So I can say that fx is continuous on minus 1 comma 1, because for every value in the interval minus 1 comma 1 the value of f of x will be defined. So you cannot say it is discontinuous at any point in this given interval. Now if I find out f dash x, see it is x to the power 1 by 3. If I differentiate, I will get 1 by 3 into x to the power 1 by 3 minus 1. The derivative of n x to the power n is n into x to the power n minus 1. So I am getting 1 by 3 x to the power minus 2 by 3. This is what? 1 by 3, power is negative, so it is 1 by x to the power 2 by 3. Clearly you can say for x equal to 0, the value of this will be undefined. So you can say fx is discontinuous at x equal to 0. Therefore f dash x is discontinuous at x equal to 0. Therefore fx is not differentiable in minus 1 comma 1. So your second condition is not satisfied, so you can say that Rolle's theorem is not applicable. But further, if you want to see, now f of minus 1, if I put minus 1 here, it is minus 1 to the power 1 by 3, it is minus 1, and for f of 1 it is again 1 to the power 1 by 3, it is 1. See, f of minus 1 is not equal to f of 1. If any of these three conditions are not satisfied, then you can say it is Rolle's theorem is not applicable. Now here in this case, two given conditions are not satisfied by the function, so you can say that therefore Rolle's theorem is not applicable. The second question is, again, show that Rolle's theorem is not applicable for the function f of x is equal to box of x. Box of x means greatest integer function. Here we know that box x function are discontinuous at all integral points, because for x equal to minus 1 the value is minus 1, for minus 1 plus it is again minus 1, and for minus 1 minus it is minus 2. So we can say that since box x is discontinuous at all integral points, therefore f of x is not continuous in the interval -1 to +1. I have already told you, if any one of the three conditions are not satisfied by the function, then Rolle's theorem is not applicable. Further, you can say that for x equal to -1, the value is -1. For 1, it is 1. So it will have different values for 1 and -1. Therefore, your second condition is also not satisfied. So clearly, you can say that Rolle's theorem is not satisfied. Here comes mean value theorem. It is also called Lagrange's mean value theorem, LMVT. It states that if f of x is continuous on a comma b, differentiable in a comma b, and f of a not is equal to f of b, then there exists at least one point x equal to c in the interval a comma b, for which or such that f dash c is equal to f of b minus f of a by b minus a. I have already discussed this chapter in my video lecture. Please go through the lecture and you'll get to know the theorems. So now, how to proceed with problems? Let me draw the graph for you. This is a function. This point is x equal to a. This point is x equal to b. So the corresponding value of function will be b comma f of b, and this point will be a comma f of a. Now they have different values. F of a is not equal to f of b clearly. If I draw the chord, now tangent at this point will be parallel to the chord AB. So this point is x equal to c. We know if I draw a tangent at the point x equal to c, it will have a slope is equal to f dash c. When I find the value of dy by dx or f dash x at any point on a curve, it represents the slope of the tangent at that point. So f dash c is the slope of the tangent at that given point. It will be parallel to the chord AB. So we know when we join two points, their slope is given by y2 minus y1 divided by x2 minus x1. So this line AB will have a slope y2 minus y1 divided by x2 minus x1. So we need to verify this. Now your third problem is verify LMVT, or you can say mean value theorem, for f of x is equal to x square minus 4x minus 3 on the interval. Now the interval is given a is equal to 1 and b is equal to 4. So 1 comma 4. Since fx is a polynomial function, therefore fx is continuous on 1 comma 4. We already told you polynomial functions are continuous everywhere. So it will be continuous in the interval 1 comma 4. Now if I find f dash x, I will get for for x square it is twice x, and for 4x it is 4 into 1. So it is twice x minus 4. Since f dash x is also a polynomial function, therefore f of x is differentiable in the interval 1, 4. Now find out the value of f of 1. Let's check the values of function at the boundary points. For f of a means f of 1, it is equal to 1 minus 4 minus 3. Clearly it is non-zero. 1 minus minus 6. And for f of 4, put 4, I'll get 16 minus 16 minus 3. I am getting minus 3. So it satisfies all the given condition. I can say that f of 1 is not equal to f of minus 3. Hence LMVT is applicable. Therefore there exists at least one point x equal to c in 1, 4 for which f dash c is equal to f of b minus f of a by b minus a. Now the value of f dash c is equal to, if I put x equal to c here, I'll get twice c minus 4. Your f of b is equal to minus 3. F of a is equal to minus 6 minus minus plus 6, and it is 1, 4 minus 1. Clearly I am getting minus 3 plus 6 plus 3 by 4 minus 1, 3. I am getting is equal to 1. So twice c minus 4 is equal to 1. So I am getting c is equal to 5 by 2. C is equal to 5 by 2, which belongs to the interval 1, 4. 1, 4. So you are correct. The value of C lies in the interval 1, 4. Hence LMVT is verified. If the value of C lies in the given interval, then we can say your theorem is verified. Otherwise we would say it is not verified. Okay. So in next video we'll upload some problems of this chapter of NCERT book.